All right, thank you so much. Good morning, everyone. I'm Eileen Ho, and I'm here on behalf of myself and Mr. Contreras, and we're going to be sharing our project on creating an intelligent mobile app that predicts pathogenic bacteria levels and water quality in inland and coastal beaches. So, to kick things off, let's start with why this work matters. So, first and foremost, monitoring water quality isn't just about meeting regulations, it's about protecting public health. And so, one of the primary strategies in water quality monitoring is the use of these indicator organisms to assess the level of water contamination. Among these, E. coli is its common name, stands out as the gold standard in the water sector. And this is largely due to its specificity in detecting fecal contamination and the ease in which it can be tested. And so what this means is that elevated levels of this bacterium are directly associated with serious health risks, including conditions such as dysentery, fever, muscular pain. And when humans do come in contact or consume these contaminated these water sources, the consequences can be very severe. Moreover, a spike in E. coli concentration can often be directly linked to the presence of other harmful pathogenic bacteria, compounding the risks posed to human health. The origins of these contaminants in water bodies are frequently linked to stormwater and sewer runoff, and these pathways allow pollutants, including E. coli, to infiltrate these natural water systems. And once these are introduced, the behavior and persistence of E. coli are heavily influenced by environmental factors such as precipitation and temperature. So, for instance, warm and wet conditions are usually more conducive to the growth of this bacterium. And this dynamic becomes very alarming in the context of climate change, as it's obviously intensifying these environmental drivers. So, over the recent decades, climate change has dramatically altered precipitation patterns and temperature extremes, creating conditions that favor bacterial proliferation. So, for example, in the Northeast United States, heavy rainfall events have increased by around 72% between 1958 and 2012, accompanied by an around 8% rise in annual precipitation since 1991. And so these projections suggest that these trends will persist, and with heavier storms, more frequent flooding, and extended periods of extreme temperatures becoming the norm, we see a magnified risk associated with these contamination systems. And the problem that we saw is that despite the urgency of this issue, our existing approaches to water quality monitoring and management still remain quite fragmented and insufficient because for one, current systems lack centralized tools and predictive technologies that we need to deliver timely and actionable insights about water contamination events. And because of this, public health systems are often left to respond reactively and to address contamination only after it has impacted communities. And so this reactive posture is both inefficient and leaves vulnerable populations at greater risk, especially those affected by climate change and resource constraints. And so, in light of these challenges, it became clear to us that there needed to be some kind of solution that could provide proactive results rather than reactive ones. And so, ultimately, our goal is to build a future where water quality monitoring is about anticipating and preventing crises instead of managing them. So our application introduces a solution that leverages machine learning and mobile technology. So specifically, we developed a mobile application and chose an algorithm that could best predict and display pathogenic bacteria levels and overall water quality. So as I was saying, currently water quality data is reactive. So usually the standard is that testing is conducted periodically and results are often lagging behind the actual moment of contamination. So think every couple of days, someone will go in and test the water quality, and then it will be updated. So if your water quality changes between that interval of, let's say, 3 days or 7 days or more, then you don't have a good measure on whether it's safe in that gray area. So our application, as I was saying, offers a proactive alternative. So instead of, you know, testing every week or every couple of days, we will be continuously analyzing water quality data. And so it will provide real-time and forward-looking insights that can warn people ahead of time and help fill in that knowledge gap in those gray areas. And so this allows for earlier notifications or warnings to the public authorities and creates a larger window of opportunity for these preventative measures. And ultimately, this approach enhances public health by promoting quicker, informed responses to these potential contamination risks. So, one key feature of our application is accessibility. So while water quality can often be available online, it's honestly quite difficult to locate or understand for many individuals. And so our application tries to serve as a sort of centralized spot to make the information more accessible in a clear, user-friendly format. Moreover, our application is scalable, meaning we can apply it to many locations. So as long as we have the data, we can apply it to areas where maybe they lack testing infrastructure, whether they're urban centers or rural areas, and places that can benefit from these pieces of data. And so, in summary, our machine learning based solution is designed to complement the traditional testing methods. So it's not to say that, you know, this application should be used instead of testing. It should be supplemented so that we're filling in those gaps of knowledge. And so by making this health information more accessible and also actionable, it allows communities to implement more effective water quality management strategies. So together, we are aiming to safeguard public health in a very proactive, efficient manner. So there were some challenges in development, which I'm going to go over and explain. So for one, as we were collecting and processing our data, we found some challenges in grouping our data. And so because water bodies vary significantly in size, location, susceptibility to contamination, this variability introduces some risk of statistical bias. And in addition, we saw that there were irregular sampling intervals that skewed the analysis. And so to address this, we were proposing to use resampling methods. So we would aggregate the data in a way that could ensure uniform assessment across different water bodies. So for example, when we were talking about our temporal frame with the dates, we made sure to reorder the data so we had data from every date. In addition, so variability, and then the final one was user accessibility. So we wanted to make sure that the way we were presenting the data, which was often quite complicated, could be in a way that users would understand, and that we were highlighting visual representations of the data, like charts and maps, and making sure that we had things like timestamps and confidence predictions so that we were accurately displaying this information to our app users. So in terms of our system overview, we had a couple of components that we used. And so the first component in our application is our prediction algorithm. So we trained the data using the Massachusetts Department of Public Health public beach information, which included a subset of around 100 beaches that all had a variety of data in there. And so, for example, indicator levels, location, beach type, all of these that help provide some comprehensive insights into water bodies across the state. And so this was all publicly available data, which we use to train our algorithm. The machine learning model itself is based on a support vector machine, which operates through an AI server built using Python's Flask framework. And so the process, more simply, is that the user requests water quality information, which sends a GET request to our AI server, which includes details like beach type, location, etc. And then once we process this data, we respond with an approximation of the microbiological water quality, indicating whether it exceeds the safety thresholds of whatever local area you're in. And so we return this output as a JSON file, which is parsed and then presented to the users. And so we decided to use this system because it allows us to provide reliable real-time predictions for the location and time. The second main component that we focused on for our application is data collection and processing. And so this is focused on gathering and processing the data necessary for accurate predictions. So our application integrates location data using Thunkable's Google Maps feature. So when a user enables location services, the app identifies water bodies within a 10-mile radius and fetches the relevant information. And then our collected data is formatted into valid parameters and assigned variables for processing by machine learning model. And so this ensures that it's compatible with our predictive algorithm. And in addition, by streamlining this data collection, users can easily access information about nearby water bodies without manual searches, enhancing convenience and accuracy of the system. And the final component that we focused on is data presentation. So the third component is how we display the results to users. And so we prioritize making complex data accessible regardless of a user's scientific background, as I mentioned. And so our app tries to provide the information in a clear presentational format. And so some of the key features are viewing the data on a map, the map interface, which allows them to, find their location easily, look at nearby beaches easily, as well as the list view, which allows them to search or to sort by name or location. And in terms of our development platform, we built the application on Thunkable, which allows easy block-based coding that integrates tools like Google Maps and allows for a user-friendly and presentable application. Yeah. So to ensure that our application was going to be most effective and most reliable, we conducted several experiments. And so for the first one, we focused on understanding the correlation between dates and temperature. And so we basically took all our data that we had from the MDPH, included a couple hundred of entries spanning many dates, and then by plotting E. coli levels against the temporal framework, we could see around at what time we would see these E. coli levels spiking. So we typically saw it spike closer to the summer, with the median at July 26th. And so the spike coincided with season's highest recorded average temperature, suggesting that potential link that we talked about between climate change and E. coli. In addition, we made sure that to test the app's accuracy against our own data. And so we tested the app by comparing its predictions of E. coli data with the raw data from the MDPH. And so the app's predictions were evaluated across beach types, marine, freshwater, and over a variety of test locations. And we saw that across 50 locations, we saw a prediction error of around 2 units, demonstrating that it was relatively reliable in terms of this case. Yeah. Before I move on, I want to talk about 2 other experiments that we did. So as you can see on the graph on the right, we also did several experiments that tested which algorithm works best for our application. Yeah, so which algorithm returned the highest results for E. coli, or I should say the most reliable. And we tested between linear regression, polynomial regression, and the support vector machine. And we could see that the support vector machine was very accurate in predicting the E. coli levels, much more so than linear and polynomial. So there are a couple limitations that I want to address. So for one, there are some geographical scopes that we want to expand, because right now our data set is restricted to Massachusetts water bodies. And obviously, if we're going to scale this up, we're going to have to gather data from other places. But I feel that this should be relatively simple as long as we find a repository for this data, as well as analyzing their guidelines. Yeah. Um, Two other ones are that we want to include additional indicators. So there are a couple ways of monitoring water quality, and so uh, this could be fecal coliform. This could also be total coliform. And given these different parameters, each kind of requires a different analysis, because each signals for a different level of action. So for example, total coliform, only 30% of that is pathogenic. And so we would have to take that into account. And finally, we would be very excited to explore additional environmental factors for a deeper analysis. So past temperature and precipitation, we could factor in other things like the surroundings nearby, or the other climate patterns that we're not using. So, to conclude, we conducted 4 experiments to better understand and validate our system's performance: temporal correlation, temperature correlation, predictive accuracy, and algorithm accuracy. But yes, machine learning is amazing in that it enables proactive real-time water quality monitoring, and we hope that as our application continues to develop and continues to grow in accuracy, we can use this to supplement the current water quality monitoring that we have today, in order to create a more robust system of protecting public health. Thank you.